Right, this is part 2 of the notes we did on Wednesday. And we started off with solutions. It's a homogeneous mixture of two or more substances that are in a liquid phase. Now, the solvent is the dissolving medium, otherwise known as the thing that's doing the dissolving. This is usually the liquid. And the solute is the substance that's being dissolved, and this is usually going to be a solid. At this point, what we did is we stopped and watched a video, and you can find the video. It's in Edpuzzle. The link for it is in Google Classroom, and that was rate of dissolving. So if you haven't done that Edpuzzle, be sure that you've got that done. I did take a grade on that. All right, so agitation causes collisions between the solute and the solvent particles. You can increase the rate that something dissolves by changing the surface area. The more surface area, the faster it's going to dissolve. If you increase the temperature, remember kinetic energy is temperature. Ke stands for kinetic energy. An increase in temperature will increase a solid's solubility in a liquid. Now, this is not true for a gas. In fact, if you increase the temperature, it will decrease how much gas will be dissolved in a liquid. Let me do a little blow-up drawing here of that. So let's say I've got a glass of soda, and this one is cold, and I've got another glass of the same type of soda, and this one is warm. There's the level of fluid. And let's say that I've got carbon dioxide dissolved in there. That's what's going to give it the fizziness. In the cold, our particles are going to be moving slowly. They're going to bump into each other less often. And they're going to be able to get out of the soda more slowly. The rate that these are going to be leaving is going to be slower because the particles are moving slower. Also, if they're bumping into each other less, we can have more particles in here. Remember, these are gas molecules. In a warm solution, these particles are moving much faster. If they're moving much faster, they're going to bump into each other, and they're also going to reach the surface quicker. So these particles, more of them are going to leave. So when you're comparing cold versus warm, you're going to have a greater number of gas particles able to be present in cold versus something that's warm. Now, the other thing that makes a difference as far as what influences the rate of solubility is the substances that are involved. If they have weak intermolecular forces, they're also going to dissolve more easily. Solution equilibrium, the rate of crystallization, it's going to be reach equilibrium when the rate of crystallization and dissociation are equal. We can think of crystallization as being particles coming together or coming back together. Where dissociation is the separation of ions. Remember, ions are charged particles. So when we're looking at solution equilibrium, the rate that things are coming back together and forming a crystal is going to be equal to the rate that things are breaking apart, disassociating and separating into ions. An ionic compound is a compound that is made from positive and negative particles. Oops, don't cross the L. There we go. So NaCl is a good example of an ionic compound. When the sodium and the chlorine are bonded together, the overall charge is going to be 0. When they come apart in a solution, we're going to have sodium ions that are positive and chlorine ions which are negative. So NaCl is an ionic compound. When it's held together in a solid form, there's no charge on the particle. When it separates out, when it's dissolved in water, there is going to be charged particles in that solution. An aqueous solution is a solution where water is the solvent. Effervescence just means that it is fizzy due to the escape of gases. A surfactant is a substance that reduces the surface tension of a liquid. An example of this would be dish soap. That will reduce the surface tension of water and the other molecules that are in there, and so it'll break up oils. The next, more vocabulary words. A heterogeneous where particles in solvent are so large that they settle out is called a suspension. Muddy water is a great example. The soil is more dense than water, so gravity is going to pull the soil to the bottom. A colloid is a mixture formed from particles that are sized in between those of solutions and suspensions. The particles are small enough to be held throughout the solvent due to the movement of the surrounding molecules. And of course, solutions are going to be 2 or more substances, and that should be liquid substances, that will not settle out. Now, you can cross out these right here. We're not going to be doing any of that vocabulary. And moved back to, we started the POGL on solubility. So that's the next thing that we did. And that was the notes for Wednesday. And that is where we ended. We actually... All right, now we've got Monday. That would be October 26th. These are the notes that we did today. So we started off with strong electrolytes. These are any compound whose dilute aqueous, and remember aqueous really just means water, solutions conduct electricity well. So this means that most or all of the dissolved compound separates into ions. Remember, an ion is a charged particle. And the charges, of course, can be positive or negative. An example would be hydrochloric acid. So hydrochloric acid, when it's in a solution, here's our level of fluid, is going to break up into hydrogen ions and negatively charged chloride ions. And they're just going to float all over the place. in our solution. And almost all of these are going to be broken apart into those ions. And that makes this a strong electrolyte. You can also have weak electrolytes. These are any compound whose dilute, aqueous, or watery solution conducts electricity poorly. This means that only some of the dissolved compound separates into ions. An example of this would be hydrofluoric acid. So this is a very strong attraction for its other part. So when this is dissolved in water, some of them are going to be disassociated or dissolved, but most of them are going to come right back together. They're still going to be in solution, but they're not going to be separate ions. So this would be a weak electrolyte. And we can also have a non-electrolyte, when none of the dissolved compounds is going to have any ionic form at all. So here would be an example of a non-electrolyte, CH4. It's going to be dissolved in water, but there's no charges on any of these. Oops, CH4. And this is a non-electrolyte. Okay, so those are electrolytes. So colligative properties, these are properties that depend on the concentration of the solute particles, but not on the solute's identity. A great example of that is freezing point depression, where you have a liquid solvent and then you add solute to it, and it actually makes the freezing point happen at a lower temperature. And I'll explain that in just a second. The opposite of this would be a boiling point elevation, when a solution has a higher boiling point than the original solvent did. So looking at this, this would be the curve for water. So this would be the freezing point of water. It freezes at 0 degrees Celsius. Water boils, this is the boiling point, at 100 degrees Celsius. Now, if I add salt to the water, it's actually going to freeze at a lower temperature. So right here's our new freezing point. The same thing is going to be true if I have salt water. It's actually going to boil at a higher temperature. This is our new boiling point. So this is useful, lowering a freezing point. This is why they salt the roads. When we have a salt solution on the road, it's not going to freeze as quickly as plain water would. So when that snow hits the road and starts to melt, it won't freeze if you have salt mixed in it. It's going to freeze at a lower temperature. The same thing is true with a boiling point elevation. If you put salt in water that you're cooking your spaghetti in, it's actually going to raise the temperature that water is going to boil at. And so it's going to cook the spaghetti faster because it's in hotter water. Dilutions. If your tea is too concentrated, let's say that you've added too much sugar, you would add water to dilute it down. This does not change the number of moles of solute. You're still going to have the same amount of sugar. You're only changing the volume that it's in. So concentration is equal to the number of moles divided by the volume. Now this is different than molarity. Molarity is the number of moles per 1 liter of our solution. So this volume can be any number. When we're going to calculate dilutions, it's an easy formula. It's the concentration at the start times the volume at the start is equal to the concentration at the end times the volume at the end. And this looks a lot like a gas law problem. P1 V1 equals P2 V2. So when you're going to do dilution problems, it's kind of a three-step thing. The first thing you want to do is convert volumes to liters. So if you have milliliters, you're going to need to convert it to liters because our concentration is usually going to be in molarity, which means liters. So convert the volume to liters. The second step is read carefully. Two determined volumes. So this would be V1 and V2. The third step would be just to substitute the numbers into the formula and solve. And then we did 4 different examples of how to solve those types of problems. The last thing we did is we talked about precipitates. This is a solid that forms, or solids that form, when 2 liquids are mixed. And right here what we've got is a solubility table. You'd never need to have to memorize this, you would always be given it. So you can see that some compounds, no matter what they're mixed with, are always going to be soluble in water. They're always going to dissolve completely. This would dissolve, and this would dissolve, and this would dissolve. Get down to the bottom here, and you can look at something like bromine. Bromine is going to dissolve unless it's mixed with something that contains silver, lead, or mercury. If it combines with those things, it's going to settle out and form a precipitate. So here's an example. Barium is going to produce positive ions. Bromine is going to be negative ions. So here's my solution. So I've got my ions floating around in here. Okay, that's the barium bromide. Here's my other solution, silver, which is going to have a positive ion, and nitrate is going to have a negative ion. And again, these are going to be floating around. They're completely disassociated. Remember, that means that they are broken apart into their charged parts. And they're just floating around there. Now, if we mix the 2 of them together, I've got to have a bigger beaker because I got to pour that volume in. I'm going to look and I'm going to see that here's bromine, and it is being put in with silver. So what's going to happen is the silver is going to combine with the bromine, and it's going to form a solid that's going to settle to the bottom. That's our precipitate. Like that. Now, the other ions are still going to be in this solution, but they're still going to be floating around. There's a barium, there's a nitrate, there's another barium, there's another nitrate, and so on. I could just keep doing this all day long. But you get the point, okay? This down here is the solid that formed. This is the precipitate, which is a solid. And there you have it. We crossed off the rest of these notes. We're not going to do net ionic equations. So that stopped the notes for today.